Change in free energy and the work that a system can do, there's a definite relationship between the change in free energy and work. So if a reaction is thermodynamically favored, the change in energy is equal to the maximum amount of work obtainable from the system as the process takes place. So if the reaction is thermodynamically favored, then the change in free energy is equal to the amount of work that's being done. However, in reality, there's always just a little bit amount of work that's wasted as heat, but there's not much we can do about that. Now, if a process is not thermodynamically favored, the change in free energy is the maximum work that must be done to the system as the process takes place. So that means that the change in free energy is going to be equal to the work max again, but in this case, more work must be put in order to overcome the work that's wasted as heat. So what that means is that we have to put in a lot more energy to make this reaction happen, and as a result of that, the process is not thermodynamically favored under standard conditions. If the change in energy is equal to 0 at equilibrium, then no work is being done. Now, this particular example right here, at the beginning, we have gas with a very, very small volume inside of a cylinder with a piston in it, and over time, as the reaction occurs, the gas expands and the piston moves from here to here. It expands to fill the size of the container. As a result of that, the mass that was attached to the piston is raised up. So in this case, the change in energy was greater than the amount of work that needed to be put in, and as a result of that, work was actually being done. Does that make sense? This is not a super large focus of this particular class, but you just should be aware of it. Questions? Yes?
So, for both when it is and isn't thermodynamically favored, you are putting work in, but then...
Well, when it isn't thermodynamically favored, you are putting work in. When you're not putting, when it's thermodynamically favored, you're not putting work in, but we are losing some work as heat. Now, the free energy change to the equilibrium constant at standard conditions. So we've used the equilibrium constant earlier. We calculated it. We did a lot of fun things with it. But now we have to see how the free energy and the equilibrium constant are relatable. So in this case, it measures the reaction direction, so the two can definitely be related to one another. So the formula that you will get on the AP exam is the change in free energy is equal to negative R times T, and then the natural log of the equilibrium constant, where this R is the thermal gas law constant. Which you may remember to be 8.314 joules per mole per Kelvin. So for this equation, the equilibrium constant refers to the pressure equilibrium constant and the concentration equilibrium constant in solution phase reactions. So in gas phase reactions, it's the pressure, and in solution phase reactions, it's the equilibrium constant. Now, this formula, when we go ahead and do it, allows us to see the relationship. So, what this graph is getting at here is that at room temperature, if delta G is positive, and in this case incredibly positive, 200 kilojoules, the equilibrium constant is going to be incredibly tiny, 9 times 10 to the minus 36. So what that means, if that equilibrium constant is incredibly tiny and the change in free energy is incredibly large, then this is going to be largely a reverse reaction. It will actually be a reverse reaction. There will be no forward reaction. If equilibrium constant is incredibly large, like 1 times 10 to the minus 35, and the change in free energy is incredibly negative, like negative 200, then it's a forward reaction. And if the change in free energy is 0, that means that the equilibrium constant is equal to 1, and so you are at equilibrium. So what we're doing is we're trying to tie together the equilibrium constant and the change in free energy, and eventually we'll be tying together the change in entropy along with the change of enthalpy. So all those things get tied together. Questions about that? All right, so then I'm going to walk through an example as to how this works. So it says, using thermodynamic data, calculate the equilibrium constant for the following reaction at 25 degrees Celsius. Well, at 25 degrees Celsius, plus 273 gives me 298 K. We said that we are going to be using the change in free energy standard equals negative R times T times the natural log, I don't know what that is, times the natural log of K. We said that R is the ideal gas law constant, or the thermal gas law constant. So R is equal to 8.314 joules per mole per Kelvin. But we are given our change in free energy as kilojoules per mole. So we're going to want to change one of them, and since kilojoules happens to be the currency of chemistry, we are going to change this to kilojoules by essentially dividing by 1,000. So this will become 0.008314 kilojoules per mole per Kelvin. So when I plug some of this stuff in, we know that this is going to be negative 237.2 kilojoules per mole will equal negative R, which is 0.008314 kilojoules mole Kelvin times the temperature, which in this case is 298 K, to give us the natural log of K, or times natural log of the equilibrium constant. So when I calculate all that all the way through, I end up with natural log of K equals 95.7 with no unit because kilojoules cancels out, moles cancels out, and Kelvin cancels out. So to solve this for K, the equilibrium constant, we're going to go ahead and get a value of 3.8. Nope, I lied. 3.65 times 10 to the 41 will equal K. Now, we have a negative change in free energy, and we have a really, really large K, so that means this reaction is going to be favorable. Now, the other thing that we could do with this at this particular point in time is we could say Kp is equal to pH2 squared. I don't like the way I wrote that. pH2 squared times PO2 over P of H2O squared, but because that's liquid, that won't matter, so we would really say that 3.65 times 10 to the 41 will equal pH2 squared times PO2, and from there we could go ahead and figure out their pressures and so on and so forth, although this is not asking us to do that. Any questions about that? Well then, that's approximately where I'm going to stop. You're going to have some time to work on this assignment or the other assignment for problem set 2, because tomorrow we're going to start talking about electrochemistry.